Recording now. All right, welcome everybody. This is, I believe, what, section 2.7. So, and it's transformations. I'm going to be using my calculator also. I have a graphing calculator I'm going to show you just to show you the different graphs. So we talked a little bit about y equals x squared. This is section 2.7. We talked a little bit about y equals x squared, and this is how it looks. It's a parabola. It's a U-shaped graph. And this is how it looks. Yeah, Jose, you can do that. Yeah, that's fine. All right, so what I want to talk about is transformation, moving this graph around. So this is our main y equals x squared graph. What happens if I put y equals x squared plus 5? What happens when I put a plus 5, I'm going to write this down here, a positive on the outside of the function? You see, this is the function. If I put it on the outside, I'm calling this outside of the function because this is the function. What happens when I put a plus 5 on the outside? So I want to show you that on my calculator. So here's my graph. Maybe I could do it a little higher. I got stuff all over here. There's my y equals x squared graph. There's the y equals x squared graph. Right next to it, I'm going to write an x squared graph. And I don't expect you to be able to do this, but I just want you to see what it looks like on my calculator with a plus 5 on the outside. So if we look, there's my original. There's what a plus 5 does to it. There's the original. A plus 5 raises the graph up 5 spots. Now watch what happens when I change it to a minus 5 on the outside. I'm trying to get there. There we go. A subtract 5 on the, oops. So if we put a minus 5 on the outside, there's the original graph. A minus 5 lowers the graph. What happened? Lowers the graph. Hang on. There, I don't know what I just graphed. There we go. There's the original, and there's the minus 5. It's the same graph, it's just lowered 5 spots. So that's kind of important. So let's go back to our whiteboard. So a plus 5 on the outside, a positive on the outside, moves the graph up. Y equals x squared minus 5. A negative on the outside moves the graph down. So this is plus 5 moves the graph up. And this one is at a negative 5. It moves the graph down. A minus moves the graph down. All right. So I think we have to do about 6 of these transformations. Next, I'm going to do y equals x squared, but I'm going to put a plus 5 on the inside, a positive on inside, a positive number adding on the inside. Do you see? This is on the outside of the x squared. This is now putting a plus 5 on the inside of the x squared. So let's take a look at that. So we're going to do a parentheses, x plus 5 on the inside, and then square it. So there's the original. A plus 5 moves the graph to the left. It's opposite of what you would think. You'd think it'd move it over to the positive side. But a plus 5 moves the graph to the left. Now, what happens when I change it to a minus 5 on the inside? Subtract 5 on the inside. There's the original. A subtraction moves a graph to the right. Do you see the second graph moves to the right? So that's kind of important. So a positive on the inside moves the graph to the left. If I have y equals x minus 5 and then square it, a negative on the inside moves the graph to the right. So this is a positive on the inside. This is a negative on the inside. Negative on the inside. This is a positive on the inside. It's kind of like opposite of what you would normally think. All righty, we've done 1, 2, 3, 4. Let's do 5. What about a negative on outside of function? If I just put a negative in the front, maybe I should put a negative in the front of the x squared. So a negative in the front of the x squared. Let's see what happens. If I put a negative in front of the x squared, and I hit graph, there's the original. A negative flips it upside down. Do you see? Here's the original. A negative just flips it upside down. Flips it at the vertex. All righty. A negative flips it. And I think this might be a way. There's the original. And if you look at the horizontal line here, it flips it on the horizontal line, flips it horizontal. As though there was a horizontal line there, it just flips it. Let's try a negative on the inside. Y equals negative x squared. A negative on the inside. Let's see what happens. By the way, this is going to make the workbook a lot easier. So that's why I'm doing it here. And then we'll go to the workbook, and we should be able to breeze through all of this. I'm hoping. So here's the original. I'm going to clear this and put a parentheses, negative x on the inside x square. That didn't work. Parentheses, negative x squared. All right. So graph it. There's the original, and there's the flipping. What happens is it flips it on the y-axis. Do you see? It flips. This side goes over here, and this side goes over there. So there are two graphs here. One's on top of the other. No, you don't need to buy a graphing calculator. This thing's $150. You don't need a graphing calculator. Okay. So on this one, it flips it, but on the vertical line. In other words, here's my original graph. And if I change the color, this side now comes over here, and this side comes over there. So they just flip over on one another. It's you can't see it, I mean, but it's there. Yeah, $150 is not fun. All right, so we have, I think, 2 more to do. So we have 2 more to do. I'm going to clear these if I can. If you guys, I'm going to let, if you're going to take notes, take notes. But I'm going to clear these because I need some extra room. Oh, well, yeah, maybe I'll put it down here, number 7. Yes, front and back. I think that's what you can call it. It flips over like there's a vertical line right in the center of it. The left side goes over to the right, and the right side goes over to the left. All right, so number 7, y equals 4x squared. So for number 7, it's a whole number greater than 1. So we're going to put a number greater than 1 in front of the x squared. And for number 8, I might as well do number 8 also. Did I say there's only 5 or 6? There's 8. Uh-oh. My pen. There we go. So number 8 is y equals 1/4 x squared. A fraction less than 1. So here's number 7, and here's number 8. Let's see what happens when we put a whole number, and then let's see what happens when we put a fraction. I know. Cross-eyed. All right, so let's look at my calculator. We're going to put a 4x squared. So we're just putting a 4 in front of it. Graph it. There's the original. A 4 in front of it makes it skinnier. Do you see it goes on the inside? So a 4 in front of it makes it skinnier. By the way, the book doesn't say skinnier. The book, they say it stretches it. You grab the two ends of the graph and stretch it up, and it kind of like makes it skinnier, right? You have this graph, and you grab the ends and stretch it up, and it makes it skinnier on the inside. It's called stretching it. Okay. Oh, we want to do one more now. We want to do the fraction. One fourth, the fraction part of 1/4 is 0.25. So I'm just, instead of writing an actual fraction, I'm just going to type in 0.25. It's the same thing as a fraction. It's just decimal equivalent. So if I do a decimal or a fraction less than 1, there's the original. There's the decimal less than 1. It makes it fatter. It makes it fatter. Anybody gain any weight during this COVID break that we've had? I gained 13 pounds, so I had to go on a diet. So the book doesn't say it makes it fatter. That would be very rude. So you would grab the ends and compress it down. The book talks about, or the homework might say, it's compressed. You squeeze it down. Do you see when you squeeze it down, it bulks out. It makes it fatter. All righty. So a 4 here makes it skinnier. The whole number greater than 1 makes it skinnier. But we call that stretches. It stretches it up. I don't even know how to spell stretches. 1/4 makes it fatter, but we say it compresses it. Compresses it. I think there's only one M in compress. Look at that. How did I get that? There we go. Okay, so a whole number makes it skinnier or stretches it up. A fraction or a decimal less than 1 compresses it. You push it down and compress it, and it makes it fatter. All right, that's it. That's all the transformations. That's this entire section. We know everything about this section now. All right, let's go to the workbook. Let me see if I even have it. Yes, there's the workbook. Okay, so here's 2.7 in the workbook. And once again, we're starting with our basic graph of y equals x squared. They even show you this is what the picture looks like. And just let me show you how I would graph this really quick, and then I'll move on. If you just pick some values for x, if x is 0, if x is 1, if x is 2. If x is 0, I put a 0 in here. Y equals 0 squared. 0 squared is 0. If I put a 1 in there, 1 squared is 1. If I put a 2 in here, 2 squared is 4. So 0, 0, 1, 1, 2, 2. Do you see it's on my graph? And you do the same thing with -1. -1 squared. -1 times -1 is a +1. -1, 1. -2, 4. -2 times -2 is +4. So these are the graphs. That was supposed to be 2, 4. That one. So that's our basic graph. That's our basic x-squared graph. Just wanted to show you how we got that. So here it says, describe how the graph of the equation relates to this one. So as soon as you see this, you say a -6 on the inside. On the inside, a -6 on the inside. If you go back to your notes, a -6 on the inside moves graph to the right 6 places. So if I was going to graph this, there's 4, 5, 6. That's what the graph would look like. A -6 on the inside is the same graph. It just, a negative on the inside moves a graph to the right 6 spots. The transformation is moving it to the right 6 places. That's it. Uh-oh, something's going on. My computer's making a lot of noise. Number 2, a +5, +5 on outside. If you look at your notes, thank you. Wait, Matilda, did you answer this one? This was a -6 on the inside. This is a +5 on the outside.
It moves it up.
Yeah, it moves it up 5 places. A +5, a +5 on the outside moves it up. Okay. A whole number greater than 1 makes it skinnier. Or we can say it, what did we call it? We stretch it up. Is stretch, is that stretch, or is there an A in there? No, stretches, it stretches it up. It stretches the graph up.
There's 2 T's in stretches.
Stretch, where's the other T at?
R-E-T-C-H.
R-E, no, R-E-T-C-H. Okay, that sounds good. Next, we got to talk about this transformation. It flips it, the negative on the outside, negative in front. Maybe I should say negative in front. Negative in front, flips it, remember? Flips it horizontally. And then the +5 on the inside, a +5 on inside, moves graph to the left. So this, if you look, here's our original. I'm sorry. Here's our original. And I'm going to use a different color. A +5 on the inside moves it to the left, moves it here to the left, but then it flips it. So that's, you see it moves it to the left 5 spots. That's a -5. And then it flips it. Or you could say it flips it and then moves to the left. Either way, your graph has to be over here. 5 spots to the left and then flipping it horizontally. It might be good to try to draw these when you're doing these. I don't know. Does the back of the book actually show these pictures to you? That would be nice if they showed the actual pictures so you can see them.
No, it doesn't show any pictures.
Doesn't? Okay. So number 5, if you look at this, the graph moves up, a +5 on the outside, I mean +7 on the outside, moves the graph up, a -8 on the inside, -8 on inside, moves it to the right. Moves it up and to the right. So in other words, we're going to go from here, we're going to go up 7 spots and then to the right 8 spots. There's 8 right here. Do you see it? It moves up 7, and then to the right 8. We're talking about that vertex point right there. So this moves it up and this moves it to the right. A negative on the inside moves it to the right. A negative on the outside moves it down 5 spots. A fraction less than 1 makes it fatter or it compresses. Makes it fatter or compresses. So if I do this, it's a parabola that moves down 5 spots. And we have to make it fatter, so I'm going to make it really fat. The smaller the fraction, the fatter it becomes. I know that's I mean, here's what the original is supposed to look like. That I really exaggerated the fatness there. Maybe I could have did it like this. It's still fatter than the original. Down and made it fatter. This makes it, compresses it. We squeeze it down, and the minus makes it fatter. The -5 on the outside moves it down. So now they want you to write the equation. We can do that. We know the equation starts off, this is a parabola. It starts off y equals x squared. Can somebody tell me, does this graph, remember it starts right here. Does the graph move up or down? This is the original. Yeah. So do you see it? We're talking about, we talk about the vertex point. From here, it moves up. And if you look, it moves up 2 spots. You know, this is where it starts. It moved up 2 spots. So in other words, there's a +2 on the outside. It moved up 2 spots. Then it moved which way? 1, 2, 3. It moved to the right 3 spots. See, the vertex is normally right here. It moved up 2 and then to the right 3. To the right on the inside, you have to put a -3 because a negative moves it to the right on the inside. So our actual answer will be y equals x squared plus 2, and we're going to put a -3 on the inside. This is the equation. That moves it up 2. This, a -3 on the inside, moves it to the right 3. So it says write the equation. This is the answer. Everybody okay with this so far? This section is just called transformations. It's taking a graph and moving it depending on the equation, you know, moving it up, down, right, left, compressing it, stretching it, flipping it. All right, let's try number 8. Oh no, we don't have a parabola anymore. We don't have y equals x squared, but that's okay. So we know this because we talked about this yesterday. So I'm assuming everybody knows this. Y equals the square root of x. And I'm just going to draw this for you really quick. If x is 0, the square root of 0 is 0. If x is 1, put a 1 in there. The square root of 1 is 1. Put a 2 in there. The square root of 2 is a decimal, so I'm not going to. I'll put a 4 in there. The square root of 4 is 2. Then I'm going to put a 9 in there. The square root of 9 is 3. In other words, the graph looks like this: 0, 0, 1, 1, 4, 2, and 9, 3. Remember, the square root graph looks like this, and it goes on up and over to the right forever. That's what a square root graph looks like. This is what a square root graph looks like. All right, so there's a +2 on the outside. That means it's going to go up 2. This graph is going to, each point is going to go up 2 spots. Do you see that? It's going to go, each spot, if you look at it, is going to go up 2. Each spot that I marked is going to go up 2. Then we have a -1 on the inside. A minus moves it to the right. So we're going to move to the right 1 spot. Every spot that we moved up here, I'm going to use a different color. We moved every spot. We're going to move every spot to the right 1 spot. This one to the right, this one to the right, this one to the right. Oh, and yeah, this one to the right, this one to the right. Wait, that wasn't 1. Sorry. That wasn't. Wait, where was this? That one to the right. Oh, this one to the right. Yeah, right here. That goes to the right also. And then there's one more. This one. A negative on the inside. So since it's not a parabola, it has some meaning. A negative on the in front, on the inside. Remember, we have to flip it, but we flip it vertically. So by the way, this is what my graph would look like. This is what my graph would look like if we moved it up and to the right 1 spot. You see, we moved it up and to the right 1 spot. So the graph is blue. However, so now I'm going to change my color one more time to green, dark green, because this negative, if you look, here's our line, here's our vertical line, negative on the inside, in front on the inside, flips it vertically. In other words, it's flipping here, it flips to the other side. You see, this one just flips on this line, it just flips right over. So our answer is this graph. I mean, I could have drew it a little bit better, but that's it. I'm going to erase everything else. And then I messed it up by erasing everything out. Can I bring something back? I don't know if I can. So what happens? We moved it over 2 and over 1, and then when we did all that, we flipped it, and that's what the graph looks like. And by the way, let's see how accurate we are. I'm going to put this in my calculator. Let me put it in my calculator first. Square root of x, and then I'm going to put the other one. Square root negative parentheses x minus 1. Oh, I didn't put square root in there. Square root negative x minus 1. Close the parentheses and then add 2. Okay, let's take a look at this on my graphing calculator. So there's the square root. There's a square root with the negative in front, the minus 1, and then the plus 2 on the outside. And when I hit graph, there's my original square root graph, and there's the other one. Do you see? It's up 2 over 1, and then we flipped it on the vertical line. We flipped it over. Perfect. Everybody okay with that? So even those square roots, do you see, are a different function, the transformations are the same. The transformations still work. All righty. What is this symbol right here? What are those lines? Here's my parent function. I call it the parent function, this our starting point. What do we call those lines? What have we talked about those? I think we talked about those at the beginning of the course. What do we call those lines? Anybody know?
The absolute value.
Yeah, they're the absolute value. Thank you. I just want to make sure you guys are awake. They're the absolute value function. Okay, so it's an absolute value function. The absolute value function, let me just draw the graph and show you what it looks like. If x is 0, you plug a 0 in here, the absolute value of 0, the one y is 0. You put a 1 in there, absolute value of 1 is 1. 2, absolute value of 2 is 2. Negative 1, the absolute value of negative 1 is 1. Whatever you put in there, it pops out as a positive. If I put a negative 2 inside the absolute value function, a positive 2 pops out. Always a positive number pops out when you put it in there, once you do all the math. So I get 0, 0, 1, 1, 2, 2, same on this side. You get that V-shaped graph. It's a V-shaped graph. So this is what the original function looks like. A negative on the inside, on the outside, it's a negative on the outside. It's going to move it down. And then a 2 in front of it makes it skinnier. Skinnier? Skinner. Skinnier. All right. So let's take a look on my calculator. So absolute value of x, and then we have 2x minus 7. Let me put it on my calculator before I'll forget it. If I can even put this in here. Math, absolute value. There we go. Absolute value of x. Then I go clear, math, absolute. We're going to put a 2 in front first. 2. I'm going to show you here in a second. X and then a -7. All right. So there's my absolute value function. There's a 2 in front and a -7 there when I hit graph. There's my absolute value function, and it's down 7 and it's skinnier. It's not skinnier by much, but it is skinnier. Watch what happens when I make the number larger. I mean, the larger the number outside this 2, let's say I make it a 9, it becomes even skinnier. You see, there's the original. And you see how skinny that becomes because the number's larger than 1. When way larger than 1, it becomes even skinnier. And remember, we're pulling it up. So we say it stretches up. We take the ends and stretch it up. All right. Having problem with this with my right tablet. So once again, this moved the graph down and this stretches it. Stretched it up. Here was the original. And we moved it down 7 spots and stretched it up a little, made it a little skinnier. All right. Yeah, this tablet is pissing me off. It's making lots of noise. All right. Uh-oh. So I think there's one like this on the test. A lot of people have problems with this type of problem. See, they don't tell you what type of function it is. They just call it a function, y equals f of x. Now, it doesn't matter. A negative in front of the function, what does a negative in front of the function do? Y equals, let's say we have x squared. What does a negative in front of the function do?
It flips it horizontally.
Yes. Flips horizontal. In other words, I'm going to just show you this dot is 1, 2, 3, 4. Now it's 1, 2, 3, 4 up here. This dot is on 0, so when you flip it on horizontally, here's my horizontal axis, it stays there. This dot stays here. This dot stays here. But this dot, when we flip it, it comes up to here, 4 up. So the graph would, I mean, just without the negative and without the, 1/2 in front, without the 1/2 in front, you see this is 1, 2, 3, 4 up. So 1, 2, 3, 4 down. This is where the graph would be. It would look like this. Do you see? It's the same graph. We just, this flips down, this flipped up, and this flipped down. Okay, so that's the flipping part. Now the 1/2, the 1/2 makes it fatter. Remember, with a large number compresses it, makes it skin. A large number stretches it, makes it skinnier. We're going to compress this and make it fatter now, but we're going to make it fatter by 1/2. So each dot that's up here, we're going to make it fatter by 1/2. In other words, we go up 4, so half of that would come down here. Do you see? We're only going up 2 now. If we did that, it'd come down 2 spots right here. So I'm going to erase the red graph and show you. Oh, by the way, that would come down to 4, but it would only go to 2 now because it's half of it. So each dot that we move is half. By the way, half of 0 is still 0. That's why these stay here. And half of 0 here goes 4, so we put the dot here. I shouldn't have erased it. So now it looks like this. Let me show you what it looked like before we compressed it. It was like this. Wait, it was like it, then it went to here. Do you see? The blue was before we took the 1/2. The red is 1/1/2, and if you notice, it kind of we compressed it. The a fraction we compress it. We take this top and we push it down. We take this and we push it up. We're compressing it. So the 1/2 compresses it. The negative flips it horizontal. And it compresses it by a factor of 1/2. If it was 1/4, then we'd have to divide each point by 4. Do you see? This is 4 high, then it would 1/4. It would compress to 1. Do you see? From 4 to 1, it would be definitely more compressed. All right. This is an absolute value function. It just says describe the transformation, absolute value of x. Anytime you have a V-shaped graph, it's an absolute value of graph. Somebody type in what the transformation is. You don't have, use parentheses instead of the absolute value. Use a parentheses. Yeah, use a parentheses. So when you type it in, just type it in with parentheses and tell me what your transformation is. See if you can type it into the chat box. Remember, absolute values always start, everything starts at 0, 0. It starts at 0, 0 at the origin on our graph. See if anybody can type in what this transformation should be, what the equation should equal. Anybody have an answer? Give up. Well, we know it started, you know, the vertex, the pointy part started right here, right? It starts at 0, 0. All our graphs start at 0, 0. So this graph, to get to this point, we go 1, 2, 3, 4. We went down 4. Then we went 1, 2, 3, 4, 5. We went to the right 5. Well, down 4 means you put a -4 on the outside. Remember, a minus on the outside means we go down 4. And to the right 5 is a -5. So this is what the absolute value function would look like. That's it. You know, the graph starts right, you know, right here. The whole graph went down 4 to the right 5, and that's it. Does everybody see that? You know, your graph always starts in the center at 0, 0. And then you have to determine the transformation to where it goes. Good, good. Because that was the last one. Of the transformations. So definitely, I mean, don't wait till the weekend to do your homework. Please, I beg you, stay current. There's a lot of homework this week. There's quite a bit of homework this week. We still have some more to do down here, but these are not transformations. This is something else. How many do we have? 12, 13, 14, and 15, 16. Okay, so I think I need to do number 13. I'm going to do number 13 first. Okay, so yes, I'm going to do number 13 first because number 12 is a bad problem. It's not a bad problem, it's just weird. I'm going to show you that, but number 13. Let's read the instructions. I keep on going back and forth. I'm getting dizzy. It says determine if the following are symmetric with the x-axis, the y-axis, or the origin. So we just need to know if they're symmetric with the x-axis, the y-axis, or the origin. Okay, the origin is the center. The origin is the center. So let's look at number 13 first. What does symmetric mean? It says, let's see if it's symmetrical. What does symmetric mean? Symmetrical, when they say, haven't you ever seen, yeah, same on both sides. Thank you, Alma. Haven't you ever seen like, they're determining the most beautiful people in the world or something like that, and they look at their face and say that person's face is perfectly symmetrical. In other words, the eyes on the same spot on both sides of the head, and one's a lot higher. Or your eyebrows, you know, you ever see somebody with eyebrows one higher than the other when they get it tattooed? That's not symmetrical. It's not the same on both sides. Sorry if any of you have your eyebrows tattooed and they're not symmetrical. Okay, I want everybody to take a picture of their face and send it to me so I can determine if your face is symmetrical or not. Especially if you got tattoo eyebrows. All right, so we want to know if it's symmetrical with the x-axis, the y-axis, and then the origin. Here's the x-axis. I'm going to draw a line through the x-axis. Is the stuff on top look the same as the stuff on the bottom if I flip it? Does it look the same? Yes or no? If I flip this down to the bottom, does it look the same down there on the bottom? No, because this has a closing spot. There's no closing spot down here. So with the x-axis, do you see the x-axis? It's not symmetrical. It's not symmetrical. The y-axis, this is the y-axis. And another way of saying symmetrical is the mirror image. Do you see if I fold this over now on the y-axis, when I fold it over, does this side look the same as that side? Yes. When you fold it over, both sides touch each other. So yes, it's symmetrical. So the y-axis, it's symmetrical because it folds over. Now the origin is a really tough one. Is it symmetrical with the origin? In other words, there's the origin. If I rotate this around, if I take this graph and rotate it around, does it look the same all the way around? Is it in the same spot all the way around? And no, it's not. No, it's not symmetrical. It's not symmetrical with the origin. So this graph is only symmetrical with the y-axis. With this y-axis. If I fold them over, they both touch each other in the exact same spot. With the x-axis, it doesn't touch, you know, with the x-axis, it doesn't fold over. This part doesn't touch anything over here. It has to touch the same thing, and it doesn't. So it's not symmetrical with the x-axis. It's only symmetrical with the y-axis. All right, so I'm going to go to number 14 now. And if I look at the x-axis, let me erase these. If I fold this over on the x-axis, do I get the same picture when this comes down here? No. You see, there's no graph down there. Or what if I put this up there? There's no graph up there. So it's not symmetrical with the x-axis. No. Let me just put no. The y-axis, here's the y-axis. If I fold this over, you see it's 2 spots this way. So 2 spots this way, is there a parabola there? And no, it doesn't. If I fold it over, it doesn't line up. It doesn't line up perfectly. So it's not symmetrical. And the origin, if I rotate this around, it's not symmetrical either. So this is not symmetrical with any of the axis or the origin. Number 15. Maybe I should have did 15 first. That's the best one. Here's the x-axis. If I fold this side up that way and I fold this side down that way, does the graph look the same?
Yes.
Yes. So it is symmetrical. With the x-axis. So now I'm going to do the y-axis. If I fold the graph over to this side and this one over to that side, does it look the same?
Yeah.
If I fold it like a piece of paper, they touch each other. It's the same. So yes, it's symmetrical with the y-axis. And finally, we get one with the origin that's symmetrical. Here, look at this graph. If I rotate it around in circles, does it look the same? If I, do you see if I turn this graph around in circles, does it look the same around the origin? It does. It's a circle. If you rotate it, it's still the same circle. So yes, it's also symmetrical with the origin. So 15 is yes, yes, yes. Let's go back up to 13. Oh, there's a 16 here too, but let's go back up to 13 first if I can get there. Oh, 12, I mean. Here's the x-axis. And once again, if I flip this up here, it doesn't look the same, and flip this down there. Well, if you flip it on the x-axis, it's not going to be the same picture. So no for the x-axis. It's not symmetrical. If I do the y-axis and I flip this to that side and this to that side, it doesn't look the same. I'll flip it over, it's not the same. So no to the y-axis. And once again, if I rotate it, it doesn't look the same. So no to the origin. It doesn't look the same either. So number 12 was no, no, no. Maybe I should have did the circle first. That's it has to look the same. And I think there was one more. Yes. If we look at it on the x-axis, if I take this to the top and that to the bottom, does it look the same? If I flip it on the x-axis like a piece of paper just folded over, and this is the fold, you know, this is the fold right here. Do you see how it folds over on itself? So yes, it's symmetrical with the x-axis. On the y-axis, here's the y-axis. If I fold this over, there's nothing to fold back over, so it's no. Do you see? It's not the exact same picture if I fold it over on the y-axis. So no, it's not symmetrical. And then finally, with the y-axis, and no, it's not symmetrical with the origin, because when you rotate it around, it's not the same picture all the way around. So symmetrical with the x-axis, you have to fold it along the x-axis and you should get the same picture. Symmetrical with the y-axis, you fold it along the y-axis and get the same picture. Symmetrical with the origin, if you turn it all the way around, the graph all the way around, does it look the same no matter where you turn it around in circles? And if it does, then it's symmetrical with the origin. If it doesn't, it's not symmetrical. And that is, what section did we just cover? 2.7? I think.
Yes, 2.7.
Yeah, 2.7. Any questions? So that's all I'm going to cover today. Did it say it's recording? Did I even record that?